We started this class without any assumption that you have a strong background on linear algebra, right? If now you look back, you actually learned a lot already. Particularly, we try to use quantum computing as an example, right? The most important thing we have learned is, well, any state of a system is just a vector. So memorize this. Any state is just a vector. A vector is just a name, right? Just like my state, I'm happy, I'm sad. Everyone in this classroom, we combine together becomes a vector of the whole classroom, right? A state. That is a state. And then for every state, you do have some basis if you want to, because if you want to express it, for example, I buy a dozen of eggs, then you can say I have 12 eggs, or I have 1 dozen eggs. 1 egg is the basis of one basis. 1 dozen egg is the basis vector of another basis, right? So we talk about that. And because of this, we can write the vector as a column form. Very important is that each vector, each number here represents how much components you have for the first basis. Maybe I call it 0. I just make it simple, call it 0. I can call it the first basis, the 0th basis, or whatever. Here, A1 is that how much components I have in the second basis. So in principle, I can write A equals to A0, 0 plus A1, 1 plus all the way to AN, N, right? So this one, I did not do it well. It's an old slide. How many dimensions do we have here? N plus 1, because I did not write it well. Usually people will just write A0 to N minus 1. So here we have N plus 1 dimension, right? So you realize that all the vector can be expressed as a linear combination of the basis state, okay? And here we learn 2 things. One is the inner product, right? The inner product becomes very easy if we realize that we are using a orthonormal basis. It will be just equals to the bra version times the cat version of that vector. For the bra version, how do we do it? For example, this is the cat of A, right? And then the bra is going to be complex conjugate and transpose, right? Always remember this. So I do the transpose first, A0, A1, AN, and then I have this complex conjugate, right? And naturally, if you try to follow the matrix multiplication rule, the bra, for example, this one is just equals to A0 star all the way to AN star times B0 to Bn. And you do see that it is just the individual component, the corresponding multiplication of the component, and you add them together. And that is the inner product, right? And this is only correct, again, if you are using an orthonormal basis, okay? Then we talk about superposition. Actually, here already have the superposition, but let's say again, particularly in quantum computing, we're lucky we usually only deal with 2 levels, so it is 0 and 1. You can call it up and down and up, left and right, whatever. The most important is how much component you have for each basis, okay? And when we do the measurement, what happened? The Copenhagen interpretation, you will collapse the wave function. When you do a measurement, based on how you measure, right? The measurement operator, now you understand already, has some eigenvector. Those eigenvectors are the possible outcome. For example, you measure it by using the magnetic field in the z direction. Then it will collapse to either spin up and spin down, because spin up and spin down states are the eigenvector state. And they have corresponding eigenvalues, +1, -1. And eigenvalues are what you can measure, and as a result, this measurement also corresponds to the observables, right? So if I have a state which is a linear combination of 0 and 1, then naturally when I measure, it can collapse to either 0 or either 1. And we don't know which will collapse to, right? Just like Einstein said, the God doesn't play dice, but unfortunately, in this case, it does. However, although it's random, it always collapses with a probability correspond to the square of the coefficient in front of it. The square of the coefficient, you can take the magnitude and then square or do the complex conjugate and multiply to itself. That is the same, right? So that is the basics. Any questions? Yep, easy. And I just say that it needs to be orthonormal basis when you want to do this type of inner product in this way. Orthonormal means what? It means that if the two vectors are not the same, they need to be normal to each other. Just like the xy coordinates, right? I always try to think about the real space if I don't understand anything. Y is normal to x. They don't have common quantities, right? So their inner product is going to be 0. But if they are the same, means itself, then its inner product is going to be 1. So that's why this is orthogonal, yes, and normalized for this, right? But how do we normalize the vector, right? If a vector is normalized, it means that their inner product is 1, and we already see that what is the inner product, right? How do we normalize a vector? Somehow this is not in the order. Let me talk about this first. To normalize vector, all you need to do is divide it by its length. Then it normalizes, right? So remember this, right? Okay. And then we talk about the change of basis. We can, just like what I said just now, I buy 24 eggs. I can say I have 24 1 egg. The 1 egg is the basis I'm using. I can also say I bought 2 dozens of egg. The dozen is the new basis. So I can change one basis to another basis without, while the quantity, the object, the state itself is still the same. The basis is just for me to describe the object. Okay, just like I'm happy, I can speak in English, French, German, right? It's the same. And 2 bases is particularly important in quantum computing, the 0-1 basis and the plus-minus basis. And I told you earlier that we can use a fake example, a fake notation. I can draw in a 2D plane. I call this 0-1, and then this as plus minus, which is 45 degrees to each other, right? This is wrong, but turn out the math is correct for the relationship, because 0 and 1 are talking about the eigenstates. For example, in the spin, the magnetic field is pointing upward, and you do the measurement of the spin of the electron. And it only has 2 eigenvectors, either spin up and spin down, because this is the only thing we can distinguish when you measure the energy of a spin in the magnetic field pointing up. You can either get higher or lower, and these are only the 2 possible values. But at the same time, the space is isotropic. I put it means same in every direction. I can still put the magnetic field in the x direction, and I should still get the same value in terms of energy. But this time I'm going to say that the spin is pointing left and right. It's a different state from the spin is pointing up, right? So for the same state, we can describe it as in the 0 or 1 basis, or the 1 or the plus-minus basis. And we realize that 0 is just plus minus, and then 1 is just plus minus minus. And that is not difficult to memorize, because that's usually what I memorize. Plus is 0 plus 1, right? Because it is plus. And then 0, 1 correspond to plus minus. So 0 must have the plus sign, and then the 1 must have the minus sign, okay? Or you can use this figure to help you to memorize, or cheat sheet, whatever, right? With this, then in a general state, if I want to change to another basis, one of the easy way is just do substitution. Because this becomes a times 0, which is a times 1 over square root to the whole thing. And then b times 1 times this whole thing. And then you just shuffle them, you will get this one. Okay? There's a way of changing the basis, which you have done in assignment 1. Right? Substitution, exactly. Substitution. We talk about the bra-cat relationship. We understand every state is a vector, and we say it is a cat, right? For every vector, just like a human being, we have our image in the mirror. We can also create a space that has the corresponding vector in the bra space. They are not the same, but they're corresponding to each other. So A corresponds to A bra. If we scale our vector in the cat space by C, it's equivalent to scaling the corresponding bra by C complex conjugate, which makes sense because the bra is obtained by rotating the row and complex conjugate. And of course, that is also related to the adjoint matrix, right? It's all swapping the row and column and applies complex conjugate, right? And similarly, if you have a linear combination of vector, you do the same thing, but apply the complex conjugate. So these are the relationship. Now, if I do an inner product with the bra version of A on the cat version of B, is the same as the bra version of B on the cat version of A with complex conjugate. So this go back, I've been asking you, always try to recognize which one is vector, which one is number, and which one is the matrix. A and B are vector, but their inner products are the number. So definitely, you swap them, you will expect that it should be complex conjugate only, right? Then we say that I already mentioned, right? All the observable that you can measure, they are represented by some, or should they correspond to some operators. Each operator has its eigenvalue and eigen vectors, right? The Pauli spin matrix is particularly important. I will try to memorize it, right? Sigma Z, this one, sigma X, this one, sigma Y, this one. And they anti-commute with each other. Again, what is anti-commute? It means that basically, a real anti-commute is like this. Sigma I, sigma J equal to negative sigma J, sigma I. That is anti-commute. For commute, it means sigma I, sigma J equal to sigma J, sigma I. Okay? And can you tell me what is this delta Ij again? Conical delta is equal to 0. Yes. It is equal to 0 when I not equal to j, equal to 1 when I equals to j, right? So basically it is saying that, well, if Ij the same, it is the same matrix, of course it won't be 0, right? You multiply yourself and then you add, make it 2 times, cannot be 0. It's just 2i. So this is an extra information, not a pure anti-commute, right? Pure anti-commute, we will just say that, actually I cannot say it, depends on the definition, but a simple way is just say you swap them, it becomes negative, right? And here I keep saying, ask yourself whether something is a complex number, vector, or matrix. For example, matrix times matrix is matrix. Matrix times a matrix. Matrix plus matrix is matrix. This side must be matrix. Okay, fortunately, I is matrix. Delta Ij is number, so is matrix. Everything makes sense, right? And the dimension we just discussed today is also important. Check all this, then you can avoid a lot of errors.
So we can just use the sigma negative sigma. prove it's anti-common.
No. Yeah. That is what I need for the homework. I don't need to do the I. Yes. But this is only for I not equal to j. Yeah. Because when I equal to j, then this is 2I minus it. This is not 0 here.
Oh.
Yeah. Okay. Okay, and this is important actually. Spin matrix in arbitrary direction. It is useful for all the quantum computing architecture you're going to learn in the future. To study the Bloch sphere and all these things, right? Even trap ions, superconducting qubit. The point is, but I particularly want to use in this class is to challenge your thinking. I want you to realize that, wow, for a space, the vector, not just that you can have complex coefficient, you can even have the matrix as the coefficient, right? So do you remember what it basically trying to say is if my magnetic field is in a certain direction, n, right, in the real space, what is the corresponding spin matrix? It's given by n dot sigma. So what is n again? nx, ny, nc. This is the real space, right? Any direction. But do you remember what is sigma? It's also a vector. Yes, it is equals to sigma x, sigma y, sigma z. Okay, the coefficient is a matrix. If we write it out, this is nx, x hat, plus ny, y hat, plus nz, c hat. You know that already, right, in a real space. But what is this one? It is really just x, sigma x, x hat, plus sigma y, y hat, plus sigma z, c hat. So if you do a dot product of this guy, and we already know that they are orthonormal, the basis nx, ny, nc, I mean sigma x, x hat, y hat, z hat. This is nothing but just nx times 0, 1, 1, 0 plus ny 0, negative I 0 plus nz 1, 0, 0, negative 1, right? And it's just a matrix. It becomes nz, nx minus I, ny, nx plus I, ny, negative nz. It is a matrix. And indeed, this is a matrix because it's an operator, right? And you can trap by making this in the z direction, this will become sigma z, x direction becomes sigma x. Yeah.
Should we put the conjugate on nx and y and z just for sake of completeness? Because they could be real.
Yes. Okay. Now, it cannot be complex because I already said this is a real space, but very good. Yes, in principle, I need to put complex conjugate, but they are real, so it is the same. Yeah. So, okay? Yeah. This matrix is very important. Okay, then we learn two types of matrix. One type of matrix is called adjoint matrix. Every is just like the bra version of vector. Every matrix also have their bra version. It's like bra version, right? The other space, right? Their mirror space. The adjoint is you do the transpose and then complex conjugate. It's the same as the column vector becomes the row vector, right? Transpose and then complex conjugate. Operation is the same. This is called adjoint. If the matrix equals to itself adjoint, is equals to its adjoint, it's called Hermitian. Okay, that's as a hint. Make sure that you understand this definition for the midterm. Okay, Hermitian. What is Hermitian? You need to know this. Otherwise, you cannot claim that you have taken any quantum computing class. Okay, good. And then we go forward. We keep going to have more bracket operation. Because we learned the matrix already, so we also have the bra version. if I have the cat matrix operating on the cat, is equivalent to its adjoint matrix operating on the bra. Okay, the corresponding. It's just like I'm rotating left is equivalent to my mirror image rotating is right. Okay, and this is another thing. Is this a number, vector, or whatever? Huh?
So, oh no, it's a scalar.
It's a scalar. We do it step by step. B is a vector. X is a matrix. X times B is a vector. Vector inner product of bra is a scalar, right? And we just say that you swap it. You just make this this adjoint and also put the complex conjugate. They are the same. It's easy to memorize, actually, in my opinion. Okay. The last thing, the next thing is the matrix diagonalization. This is important again. Do not say that I don't give you hints, right? I expect you to be able to find the eigenvalue and eigenvector. One way to diagonalize it is what? A is the eigenvalue, so matrix applied to a vector must equal to the eigenvalue times the vector itself. Then I move it to the left because A times the vector is equivalent to A times identity times the vector. So in order to have non-trivial solution, means that to satisfy this with non-zero A, not all components are zero, then we need the determinant of this one to be zero. So you need to know how to do the determinant. By doing this, you will be able to solve for A, the eigenvalue. Once you know the eigenvalue, you can continue to solve for the eigenvector. Okay. So matrix, we can represent vector in different bases, and it is the same we can represent in different bases, right? Now, for example, this is the sigma x in the sigma c eigenvector basis. It's 0, 1, 1, 0. But if I want to represent sigma x in its own eigenvector basis, it is 1, negative 1, which is normal. We already learned that all the matrices are diagonal if you represent them in its eigenvector basis. And this value are their eigenvectors. Okay, so I hope you can memorize this. Then another property of the matrix is called unitary matrix. What is Hermitian matrix again? It is adjoint equals to itself. This is different. Here it says is adjoint. Do I do something wrong?
Was it transfer?
Oh, yeah. Huh?
I think it was U dagger equals U inverse.
Exactly. I think I did something wrong here,
So
right?
this should be-
Yeah, I'm sorry for that. This is wrong. Should be U dagger equals to U inverse. Okay? Yeah. So I always contrast to this. The adjoint, right? I mean Hermitian self-adjoint is A dagger equal to A equals to itself. And then for unitary, it is equal to its inverse, or U dagger times U equal to I. Okay? Yeah, that is a bad mistake, but no one discovered in the last 2 years. Why is important? Yeah. I'm recording, yeah, because other students need to watch. Why this is important? Because it preserves the inner product if we do the transformation. Because this matrix, again, what is a matrix? It's an operation, a transformation, right? So if I transform F and G at the same time, then their inner product become UF and UG, right? And since UF is just equal to F U dagger, right? When I write UF, it basically saying that apply the U to the cat version and then find the corresponding bra. That is the same as finding the corresponding bra and then apply the U dagger to transform it. And so this one, you will see that UF UG equals to F U dagger UG. And because it's unitary, this is 1. That's why it preserves the inner product. Okay, I know this is a little bit confusing, right? But remember what is the meaning of the thing inside the cat? It's just of the bra is just a name. And what is this thing? You say that you apply the U in the cat first. So in the real world, I rotate myself by 90 degrees and then find the image. This is the same as I find the image in the mirror first, and then I rotate myself maybe on the other direction by 90 degrees. They are the same, right? And that's why UF and UG is just equal to UF, U dagger, UG. And this is unitary, so this is I. So unitary is very important. It preserves the inner product. Naturally, it preserves the length also. For in the basis, okay? And one more important thing is that I can write this as some column vector. It's a matrix, right? But each of these is a column vector, and they are orthogonal to each other. What I'm saying is this: U may be equals to A00, A01, all the way to maybe I use the same symbol will be better, right? This is U00, U01, all the way to UN1. Again, I should have U0N. I should have used the N-1, but here just use this. 10, U11, all the way to U1N. And then UN0, UN1, all the way to UNN, right? And what I'm saying here is this. If I treat this as a vector, then what is this? This is U0 vector. Treat this as another vector, this is U1 vector. Treat this as a vector, this is UN vector. All these vector, I can write in this way, they are orthonormal to each other for a unitary matrix. Orthonormal, what does it mean? The length of this vector is 1. You do inner product, dot product with each other, it is 0. Okay? And how do we construct the transform matrix to from old basis to new basis? All you need to do is just use this scheme. Okay? This is the basis vector, the first basis vector of the new basis. This is the old one. So new O, new, I should write 0, 0, and 1, but now it's from 1 to n. Okay, so
that's the
new
inner product.
Yeah, inner product. Yes. So the ijth element is the bra of the new I basis vector times the cat of the oj vector. Okay. We also talk about the projection operator. I'm not going to talk about degeneracy. These are old slides. We also talk about the projection operator. How do you do the projection operator? If you want to project to a base, all you need to do is just construct this matrix. Again, is this a matrix?
Yes.
Yeah, because it is the cat times the bra, not bra times cat. Bra times cat becomes inner product, right? And with this, the probability, first we can use this to do the projection. You just apply this to the vector you want to project to Vi, project any vector to the basis of Vi, and then the probability is just equals to sandwiching the vector you want to project onto there. How much was the probability, right? Earlier we talked about the if I gave you the eigenvector and eigenvalue, you can just construct the matrix from this, because This is just by definition. I mean, we derived that earlier, not definition. I derived that earlier. You can check back the slides, right? But this is a way to construct the matrix if you know the eigenvalue and eigenvector. Okay. How much more do I have? Wow, there's a lot. Hilbert space, we can forget it, right? We learned this because we want to show that we actually have been using that. Hilbert space is that it satisfies all this property, but we already know that. Of course, the length of vector is larger than 0. We already know how to deal with the complex coefficient or the coefficient when it is in the Bra space. We know how to do F when you swap F and G in the inner product, right? All this distribution law. The most important is we realize that we go to more qubits, we actually construct them from a lower dimension, and they are all done through the so-called tensor product, okay? Tensor product, then how do we do it? Again, we can ignore this. The most important is when I do tensor products, all I need to do is, this is the first one, this is the second one. I put the whole matrix to each coefficient, and then I multiply it out, right? A11 times the whole thing, A1n times the whole thing, and then I do multiplication, A11, B11, A11, B1n, right? A1n, B11, A1n, B1n, and then I form the matrix. We also learned the partial measurement. Partial measurement means that we have many qubits, we only measure one qubit. Then you will collapse only the first qubit. And only the system state that contain the first qubit to which where it collapsed to will stay there, right? For example, let's just quickly, for example, for a psi, maybe equal to 0, 0 plus 0, 1 plus 1, 1. Okay, and if I normalize it, it should be 1 over square root 3. Once I measure, maybe it collapsed to 0, then I only have 0, 0, and 0, 1 left, right? Because it will only collapse for the system states that contain the first qubit state it collapsed to, right? And if I normalize it, what should it be? 1 over square root 2, right? Okay, good. And if I give you a basis to find the matrix representation, you just use this, Hij equal to VIHJI, okay? We talk about the quantum register. I think we are very familiar with that. The most important thing is that you need to match each qubit to each other, right? So from left to right, this qubit in the first vector match to this match to this one when you do the inner product, okay? They only talk to each other. Our electron, this electron only talk to its own bra, okay? So the rest is nothing important but entanglement. Entanglement is what? You cannot simply express a higher dimension into a simple tensor product of lower dimension. You can express it as a summation of the tensor product of lower dimension, but you cannot express it as a simple one. For example, the Bell state. Finally, we also talk about why we need to be unitary by looking at the Schrödinger equation, because by itself, it mandates us to be unitary and reversible. And then we learn different type of gates, which is so easy now, actually, you think about that. But one thing I want you to always memorize, the gates is defined by how it transforms the basis vector. That's all we do. And then we come up with the matrix, okay? Remember, for example, swap gate, it means that you are going to swap the index of this basis vector, right? We have control NOT, we have NOT gate. And then we talk about the trace. We have also the phase shift gate, and also control phase shift. And also have Toffoli gate. Toffoli gate is that like control NOT. You only apply the NOT to the last qubit, if the first two qubits are both 1. And again, this row corresponds to 110. This corresponds to 111, right? And that's why the first two qubits are that, right? Talking about Hadamard gates, the most important is know that Hadamard gates can create superposition from the basis state, from the 0, right? And then even more complicated is that if applied to arbitrary states y, it also creates a superposition, but the coefficients are not the same. Okay, so that's all I have for this review. Any questions?
So this review and plus what we